So in this lecture, we'll revisit the norms for vectors. We'll also see how norms can be defined for signals basically functions with very time, and from there on, we'll look into some vector space which are given a special name known as LP spaces. Uh, so let's see for norm of vectors which are in Rn. Okay, so norm of vectors in Rn. Okay, so suppose V is some vector in Rn where V has its coordinates defined as V1, V2, V3 till Vn, where each of them are essentially real numbers, I varying from 1 to till n. Okay, so this is what essentially means when we say V belongs to Rn. The coordinates will be with respect to some axis will be this. The norm or the p norm of this vector V is defined as the following. You take the absolute value of individual components and raise it to the power p, then you add these then you add these values that you have obtained and take the pth root. Okay, so this is what is essentially your p norm of a vector. Okay, so this is the p norm of a vector v in Rn. Okay, where n is a finite integer, finite positive integer. Need not be integer in certain cases. Actually, n n is a finite positive integer. The p here is a value between 1 to infinity. Okay. Now, if you want to calculate the infinite norm of a vector, the infinite norm is defined as the max of the absolute value of all components that you get. Okay, so this is, you take the absolute value of all components and see what is the maximum of those absolute values. That is what is defined as the infinite norm. So this is the infinite norm of a vector v in Rn. Okay, and you can actually derive this infinite norm from the definition of p norm itself. So I says that you try this out and see whether you can get this or not. Now, few things to notice. As you know that the definition of norm satisfies three properties. So the p norm or the infinite norm, they'll always be greater than 0 for v not equal to 0, and norm of v will be equal to 0 if and only if v is 0. Okay, any p norm including the infinite norm. Similarly, norm of a scaled vector is same as multiplying the absolute value of the scaling with the norm of the vector. Okay, so alpha is some number that belongs to R. And finally, the triangle inequality is also satisfied by all p norms, including the infinite norm. So, norm of v1 plus v2 is always going to be less than equal to norm of v1 plus norm of v2. Okay, these three properties will always be satisfied by the norms that you take for vectors. Okay, so when I'm saying these as vectors, they are essentially some fixed vectors. Now, let's say that you have some functions, vector valued functions that map a real number to a vector. Okay, so how can we calculate the norm of those functions? Okay, so we'll call those functions as signals because they are varying in value with respect to time. So norm of signals. So suppose f is a map from R to Rn. So that essentially means that f of t is in Rn for t being in R. Okay. Now when we take a norm of f of t, so this essentially means at some given instant of t, f will have some vector value. So this norm that you are taking is that of a vector. So this norm is same as the vector norm that you have taken. So it is some p norm of the vector. So this is norm of a vector. Okay, so f of t is a vector at a time instant t, and you are taking some p norm of that particular vector. Okay, but let's say that someone says, how do you define the two norm of the signal f itself? Okay, or some p norm of the signal f itself. Okay, so these definitions are kind of derived or kind of rely on the definition for the norms of vectors that we have. Okay, so how I mean, what are these? So these are, so to understand the norm of such signals, will define certain sets. Okay, so what are those sets? Let's say we are defining a set this. So this R and Rn are basically saying that L2 or this, so we'll see what this 2 specifically means. Okay, so as of now, just see that this L2 that you have here, huh, this is a set of functions that map R to Rn. Okay, in addition to this mapping, the function f also has to satisfy some additional conditions. And what are those additional conditions? Is a collection of all those functions that map R to Rn such that integration over the interval minus infinite to infinite, norm of f of t, suppose you take a 2 norm of f of t and you square it. Okay, so integration of 2 norm of f of t squared dt is going to be less than infinite. Okay, so suppose you have a function with you. What you do is you calculate the 2 norm of the function at a given instant of time, so that is at a given instant of time. Okay, and then you square it. Okay, once you square it, you take an integration of this particular expression that you have got over the interval minus infinite to infinite. Okay, so and then you see whether this integration that you have done is going to give you a finite value or not. If it is going to give you a finite value, which is basically as infinity, then the function f belongs to this L2 set. Okay, also known as the L2 space. So this essentially is a vector space. Okay, now the two that you see here, the two that you see here appearing in the subscript of the L corresponds to the 2 that you have taken here. If I say L3, then f of t power, the norm of f of t, any norm that you want to take of f of t has to be raised by power 3. But if you see this 2, this can be any norm. This is just a vector, this is just a norm of vector, and it can be any value. For example, if I say L2 R Rn such that f is a function that maps R to Rn such that minus infinite to infinite norm of f of t. Now which norm of f of t? I'll say infinite norm of f of t squared dt has to be less than infinity. So notice here the 2 here and the 2 here. So the 2 in the subscript of L2 corresponds to the power that you are actually taking. Okay, irrespective of what is the pth norm, p norm that you take for f of t, it's the power that you take matters. So in this case, these two that you see are the same sets. Okay, it really doesn't matter what do you take here, the sets are the same, the functions will be the same. Okay, similarly L2 set or the L2 space for functions mapping from 0 to infinity to 0 to infinity to Rn. So again, if you see this is defined as f being a function mapping from 0 to infinity to Rn such that integration 0 to infinity norm of f of t, I can write this as some infinite norm of f of t squared because it's a L2 space that we are talking of. So squared dt has to be less than infinity. So now you notice another thing. The domain from which f is mapping acts as the limit of the integration for the definition. Okay, in the earlier case the domain was the entire R, hence the integration was from minus infinite to infinite. Now the domain is from 0 to infinity and hence the integration is from 0 to infinity. Okay, so you have got a name for this particular condition that you are actually seeing. Okay, so this is just for L2 space. I mean, I'll give you a general definition for the LP space as well. So minus infinite to infinite norm of any p norm of f of t squared dt less than infinity essentially means that the function f is square integrable. Okay, so if the function f is square integrable, then it belongs to the L2 space. Okay, so for for a function mapping from R to Rn to belong to L2 space, it has to be square integrable. That is what essentially this is saying. Okay, now this is where we'll come to something known as the LP norm or L2 norm. So since we are discussing L2 here, we'll come to something known as L2 norm of the signal. Okay, so I'll make a correction here. This one I'll not write as norm of f2, rather I'll put it as L2 norm of f or LP norm of f. We'll not discuss the LP norm, so we'll discuss after we discuss the L2 set. Okay, so for f belonging to L2, okay, let's say f belongs to L2 R2 Rn, then norm of f, the L2 norm of f is defined as integration minus infinite to infinite norm of ft squared some p norm of ft, which is squared dt raised to the power half. Okay, so the L2 here, as I had said, corresponds to this, but also corresponds to this when you are talking of the norm itself. Okay, now because f belongs to the L2 space, the argument inside the square root will always be finite, and hence the square root itself will be finite. So you have a valid norm that you have. Okay, this is the L2 norm. Now you should note one thing. What the L2 norm, the value that you get for the function f depends on what p norm you have considered. What p norm is considered for the vector f of t. Okay, the norm value changes with change in p, but until this square roots are there, irrespective of what p you take, the L2 space remains the same. Okay, so the L2 norm value depends, but the L2 space, L2RRN space does not depend on the p norm of f of t. Okay, so the norm value will change with the change in p. If you choose a different p, you will get a different L2 norm value. That is for sure. But if you are constructing the entire L2 space, it really doesn't depend on what p norm that you take for f of t. No matter what p norm you take for f of t, L2 space remains the same. Okay, this is one major thing that you should actually understand. So in general, LP RN space is defined as f mapping from R to Rn such that integration minus infinite to infinite some norm of f of t, or rather I'll use q here, some p norm of f of t raised to the power q dt is less than infinite. This is the LQ subspace. This is the LQ vectors, LQ space that you essentially have. Okay, and depending on what p that you consider, the LQ norm is defined as integration minus infinite to infinite norm of f of t p raised to the power q dt raised to the power 1 by q. So take a qth root is what is the LQ norm. Okay, so if you want to compare the norm values of two different functions belonging to the LQ space, remember that you have to take the same p norm for the vectors. Okay, you cannot take one norm for the vector and two norm for another vector and then compare their norms, compare their Q norm, LQ norms. Okay, so if you want to compare the LQ norms of function f and a function g, then for both function f and function g, the p norm that you take for f of t and the norm that you take for g of t should be the same. It should be the same p. Otherwise, you cannot compare. Okay, this is in general for q being less than equal to 1. Okay, for now, the L infinite now, or the L infinite space mapping from R to Rn is defined as all those functions that map from R to Rn such that is something known as the essential supremum for all t belonging to R. For all t belonging to R, f of t must be greater than infinity. Sorry, must be less than infinity. Should be finite. Okay, and the L infinite norm of f is defined as the essential supremum itself. This can be some p norm that you have decided that you want to stick to. Oh, this one. Now, what is essential supremum? So, supremum for over the entire time interval is basically if the function is, I mean, the maximum value, not the maximum, the minimum value that acts as a upper bound on the function. Okay, that is what the supremum essentially means. The minimum value that acts as a upper bound on the on the p norm of the function taken at every instant of time. So at every instant of time, you will basically calculate what f of t is and take a p norm of the f of t. Once you take the p norm of f of t, you will basically see that what is the maximum that it can obtain if there is a max, or what is the minimum value that can upper bound these particular norms. So that is what is the supremum. Now this essential supremum is something which is really funny. Okay, so I'll explain what it is through a scalar function. So let's say that n is equal to 1. That makes it easy to understand. So let's say that f is a function that maps from R to R, right? And if I plot f, or if I plot the norm of, let's say I plot f, so f of t and this, suppose this looks like this. Okay, over the time interval, so this part keeps on decreasing. So the maximum here, which is same as the supremum in this particular case, occurs at this point. So suppose, so this is the line below which, now here the f is always positive, so you can take the norm of f of t, in this case will all the function f of t itself. So let's say that this is going to be 5. So in this case, norm L infinity will be 5. Okay. Similarly, let's say that we have another example. I'll plot the mod value directly. Uh, Suppose the function is like this. Okay, this is how the norm looks like. So what is happening here is, let's, so the function f is uh, such that, let's say this value is 2. The function f is such that it will tend towards 2. The norm or the mod of f of t will tend towards 2 as t approaches infinity or minus infinity. Okay, this is how the function f is. This is the point 0. Okay, so in this case, the maximum of f cannot be defined, the supremum that you have, and since it is tending towards 2, the minimum value that upper bounds the norm of f of t is 2 in this case, and hence the L infinite norm would be 2. Okay, so this is what the L infinite norm means. This is what the supremum means. Now what we are saying is the essential supremum. So in this case, the supremum and the essential supremums are all the same. But let's say that there is a function which looks like this. Suppose it is going like this, and then there is a sudden jump to this value, and then it returns back, and it goes like this, and then let's say there is a sudden jump over here, and again let's say it comes like this. Okay, so the jump that occurs is, let's say, at t equal to 1, and the other jump that occurs is at t equal to 3, and the value that is that these jumps are taking, let's say this is 6, and let's say this jump is taking a value of let's say 7, and here if I draw a line other than the jumps, if I draw a line, I see that the so let's say that this is the norm of ft that I have plotted. Okay, and if I draw a line other than those jumps, I see that the values of norm of ft does not cross 5. Okay, so what norm of fl infinity will be? So had it been defined as the supremum of f of t over over the entire time interval, then supremum would essentially mean the minimum value that bounds the norm. But here the minimum value that bounds the norm for all time would have been 7. So in that case, supremum is 7. But we are talking of essential supremum. So when we say essential supremum, it means that these jumps at a single instant of time do not mean anything for the calculation of norm. Okay, because this L infinite norm can be derived from the general definition of the LP norm that you had. Okay, and if you see the definition of LP norm, what is actually happening? I can write this as minus infinity to infinity some norm of f of t to the power p dt. Then this is nothing but, let's say, minus infinity to 1 norm of f of t p dt plus 1 to 1, because there is a discontinuity there. It is taking the value 6. I'll directly put 6 dt. Then you'll have 1 to 3 norm of ft raised to the power p dt. I'll say 6 to the power p dt. Then I'll have plus integration 3 to 3 7 to the power p dt. Then I'll have 7 till infinity norm of ft to the power p dt. This is what I'll have. Now in this integration, note that this will be 0 and this will be 0, because integration over a to a is always 0. So these do not have any contributions at all. Okay, so in this L infinity norm, for the L infinity norm, essentially what happens is this is defined as p approaches infinity, how the norm look like. Okay, so these do not have any contribution. So even if p approaches infinity, this anyways will not have any contribution. So these jumps at an instant of time, okay, doesn't count. So here the L infinity norm, instead of being 6 or 7, it will be 5. This is what is essential supremum. Okay, so roughly speaking, the essential supremum of f means f should have reached this value over at least a small interval. For example, I mean, even for discontinuous functions, let us take an example here with a similar function, and let's say that this is what it was. This is t, this is norm of ft that you have, and let's say the function essentially is going to look like, let's say there is a discontinuity here and the function looks like this, and then the function, let's say, looks like this is what it is. So the discontinuity intervals are, let's say this is 1, this is 2, and this value is, let's say, 7. Okay, so in this case, this small portion, I mean, is not just over an instant of time, this is over a finite time interval that you have. So the norm, L infinity norm in this case will be 7. Okay, so if this 7 would have occurred at just one instant of time, then it doesn't count, because from the definition of the LP norm, it will have no contribution in the integration itself. But now, because it is over a finite time interval, no matter how small the time interval is, it has to be over a finite time interval. So if this had been over the time interval 1 to 1.0001, then also it would have counted. No matter how small the time interval is, it should be over a finite time interval. And if that is the case, I mean, where in whichever segment you are evaluating, the segment should be of a finite time interval, and in those cases you can consider the supremum values, and that is what gives you the essential supremum or the L infinite norm. Okay, so what we saw in this lecture is what we started with, what L2 space is. So we saw what L2 R2 Rn space is, and how different p norms do not affect what the set is, but affect what the L2 norm of a function going to be that belongs to the L2 space. This is only evaluated for functions that belongs to L2 R2 Rn. Similarly, if you have L2 space for maps from 0 to infinity to Rn, then norm of FL2 would essentially be 0 to infinity norm of f of t. You can fix some p, then squared dt to the power 2. This is what the L2 norm would be for f belonging to this particular L2 space for functions mapping from 0 to Rn. Okay. Also, we saw a general definition of LP Rn, and what the LP norm essentially means for a function that belongs to this particular um, LP space. Okay, and we also saw, so similarly LP over the interval 0 to infinity and Rn, so functions mapping from 0 to infinity and Rn can be defined as f. So this LP space is defined as f that match 0 to infinity to Rn, such that the integration 0 to infinity norm of ft, the pth some pth norm of ft, I would not say p for avoiding confusion, I'll use q here. Even here, avoid confusion, I'll use lq, but in later towards the lecture we'll stick to p. So with this raised to the, so this is some p norm raised to the power q dt has to be less than infinity, and in this case for f belonging to lq, um, 0 to infinity to Rn, the lq norm will be defined as 0 to infinity norm of f of t p q dt raised to the power 1 by q. So take a qth root. Okay, and then we also saw what a L infinity norm is. L infinity norm, we the L infinite space we defined as functions mapping from R to Rn, such that the essential supremum for all t in R, or norm of ft, some p norm of ft is less than infinity, and the L infinite norm in such cases is essentially the essential supremum that we had used in the definition of the L infinity space. Similarly, for L infinity mapping from 0 to infinity to Rn, it will be defined as f mapping from 0 to infinity to Rn, such that the essential supremum of the norm of f of t, the pth norm of f of t, for all t in the interval 0 to infinity, because that is where the f is mapping from. This has to be less than infinity, and corresponding to this, the L infinity norm will be defined as essential supremum of the pth norm of f of t for all t in the interval 0 to infinity. Okay, so this is what we have. In the upcoming lectures we'll take up some examples and see what L infinity space is, which signals can belong to L infinity space or any LP space for the matter of fact, And from there on, we'll look into signals. So we'll see that very popular signals that we have actually do not belong to any LP space, and a signal belonging to L infinity space may not belong to L2 space. Okay, so what we do is we then look into something known as a extended LP space. Okay, so we do some small adjustment to the definition of the space that we have here, that extends the space so that it can encompass large number of signals that we see in day-to-day life. Okay, so we'll discuss this in the forthcoming lectures. We'll stop here. Thank you.